So now that we've simplified different kinds of radicals, we're going to take a crack at adding and subtracting different radicals. So let's just start with something simple like 5x plus 7x. Something like this you recognize as combining like terms because they have the same variable to the same exponent. So that just combines to 12x. Well, with radicals it works a lot of the same ways. So think about 5 radical 3's plus 7 radical 3's. Together that makes 12 radical 3's. Now, one of the algebraic arguments behind that is that, hey, I could factor out a radical 3 from both of them, be left with 5 plus 7, and then those are like terms I can combine. So it's radical 3 times 12. Don't stress too much about that. The goal here is to recognize that when you have these same radicals, that yes, you can combine them into one term. So the rule here is going to be to combine the coefficients, should we have any, and keep the radical. So notice that radical 3 still hangs out. So we're not adding them to make it radical 6. It stays the same. Along the same lines as how you wouldn't make that x squared, it's just 12x's. It's still x to the first power there. So let's take a look at something like radical 12 plus radical 27. So again, this is not a cube root, this is just a regular square root. The first thing we're going to do is try to break those down as much as we can. So 12, I know 4 divides evenly into it, and 4 is a perfect square, and 4 times 3 is 12. 4, when I take that out, the square root of 4 is just 2 times radical 3. For 27, I recognize that 9 is a perfect square, and 9 times 3 would get me 27. And again, the square root of 9 I can pull out, because that just becomes positive 3, and I still have that radical 3 left over. So notice here that again I have the same radicals. 2 radical 3 plus 3 radical 3. Now that they are the same radical, they weren't when I started, I can combine those to make it 5 radical 3. So that's going to be the goal for all of them. Try to simplify as much as we can, and then combine whatever like radicals we have. It won't always be the case that they are the same radicals, but when they are, we can combine them. Another example would be something like number 3, except with variables this time. So I'm going to try to do that same trick where I can break it down as much as I can, and then go from there. So 5x to the 4th and 20. 5 I don't think I could break down anymore, but 20 I recognize as 4 times 5. And again, you could try dividing a couple perfect squares into it if you're not sure. I can bring out the 4 as a 2. Right? I could bring out that x to the 4th. That's an even numbered exponent, so I could just take half of that to make it x squared. And the only thing I have left hanging out under the radical is that 5 still. So think about you've got a negative 8 on the outside here. So when you end up multiplying them, you'd have that negative 16 x squared times radical 5. So now in order to be able to combine this with my other radical, it would also have to have a 5 under the radical, and it would have to have an x squared with it too, because it works the same way as when you're combining variables. If they don't have the same variables to the same exponents, they're not like terms. So let's see what we got. Well, the 5 there's nothing we could do with, but x to the 4th should come out as just x squared, because again, that's an even numbered exponent. So I'm left with minus 8 x squared radical 5. And lo and behold, I have an x squared here and a radical 5. So now I can just combine the coefficients. Negative 16 minus 8 becomes minus 24 x squared radical 5. Let's try one more example. Something like this, where you have some odd numbered exponents under the radical. And we're going to do the same trick where we're going to simplify and then see what we have left over. Here it's a little bit trickier to think about though. So 90, well, I know 9 times 10, 9's perfect square. But remember, when we have a variable to an odd numbered exponent, the trick is just to pull one of them out and be left with x to the 6, because anytime I have an even numbered exponent, that is a perfect square. So let's see. X to the 6 is a perfect square, and 9 is a perfect square. 9 becomes 3, and x to the sixth becomes just x to the third. And I still have 10x left under my radical. So I'm hoping that at least one of these other guys has a 10x under the radical and an x cubed so that I can combine them as like terms. So 10 there's nothing I could do with, but x to the seventh, that works out the same way, where I could break it into x to the sixth, x to the first, and then take this out because it's a perfect square. So I'd be left with 5 times that x to the sixth turns into x cubed again, radical 10x. So this is looking pretty good so far. For 40, well, again, that's just a multiple of 10. It's 4 times 10. And 4 is again a perfect square. Remember, radical 4 is just 2. So I could bring that out. But I'm going to put that on the outside because I normally have my coefficients out in front of my variables. So I just multiply the 2 to the x cubed, and I have 10x left under the radical. So notice that for each of these terms, it has an x cubed times radical 10x, x cubed times radical 10x, x cubed times radical 10x. You can only combine them if they have the same variables to the same exponents and the same thing under the radical. In this case, I'm in business. So 3 plus 5 is 8, minus 2 is 6. I keep the variables, and I keep the radicals. That's if you have square roots. For something like here, where we have cube roots, you have to think a little bit harder because those cubes, those perfect cubes, are a little bit harder to find. So let's take a look at an example that works out pretty nicely. The cube root of 8x plus the cube root of 27x. Well, I actually recognize 8 and 27 both as perfect cubes. If I take the cube root of 8, I get 2, because 2 times 2 times 2 is 8. But x to the first is not a perfect cube, so I'm just going to leave that under the radical there. So when I write that, I try to be as careful as I can with that exponent, not that exponent, but the cube root symbol. And 27, I recognize again as 3 when I take the cube root, and I'm left with a cube root of x. So notice I have the same thing under the cube root sign for both of these, so I can combine the coefficients. 2 plus 3 would make it 5 times the cube root of x. So that's if they simplify nicely and we don't have to break them down. But for something like number 4, we might have to do a little bit of work first. So I've got that x out in front, times, and then I write the cube root a little bit bigger because I know I'm going to be breaking it down. Minus 2 times the cube root of, again, something that I'm going to simplify here. 16. Well, we already talked about how 8's a perfect cube, so I could break that into 8 and 2. And remember the rule for variables is that if the exponent is divisible by 3, it's already a perfect cube. So I'm just going to leave that x to the 9th hanging out. For 54, if you work with enough cube roots, you'll start to recognize that as 27 times 2. But if you don't, try dividing perfect cubes in it. Do 54 divided by 8, 54 divided by 27, until you find something that works. And again, x to the 12th, that's already something that's divisible by 3. So let's see what we have here. The cube root of 8 is just 2. And the cube root of x to the 9th is just x cubed. So if I multiply the 2 and the x cubed on the outside, think about this, you'd be multiplying the x cubed to that x to the first. So it would actually become 2x to the 4th on the outside when you add those exponents. And you still have the cube root of 2. So here's what I'm thinking as I'm going into my next radical. I'm trying to get an x to the 4th and a cube root of 2 if these are to combine. Now that won't always happen, but I'm thinking in this case it might because I already see a 2 there. So let's see what happens. 27 turns into 3 because 3 times 3 times 3 is 27. And x to the 12th, when I divide that exponent by 3, I'm left with x to the 4th. So again, I can just pull these on the outside and multiply them with that 2 that I already have. So 3 times 2 is 6, and I have an x to the 4th. And the only thing I have left inside the cube root is that 2. So it works out here again that I have the same thing under the radical and the same variable, x to the fourth, so I can just combine those coefficients. 2 minus 6 becomes negative 4 times x to the fourth times the cube root of 2. So the hardest part about these is differentiating between your cube root rules and your square root rules. So remember that when you see that 3, the different rules are going to apply there.